Welcome back to KMI Community Connect viewers. Before I start part 7 of Metabolism Made Easy, I would like to mention about something that was an oversight on my side about writing the milligrams per deciliter, the units for uric acid. So I've written it here, and so that's the number. So either 7, 5 or 3.5 milligrams per deciliter is the unit in the blood. So let's talk about how uric acid is made and what is the importance of energy connection for uric acid and how this whole thing works. So we'll start with the basic unit like I talked about in the body, which is inside the cell, which is the mitochondria, and that's the cell. And we have these battery houses, which are the powerhouses, lots of hundreds and thousands of mitochondria in each cell that make energy. So mostly the discussion that we are going to be doing today is about energy, and we all know that all nutrients make energy. They produce energy, and we need energy, and the energy is made in the mitochondria, to say it again. So the unit of energy is what we call as ATP. Now adenosine tri is 3, phosphate is obviously the self-explanatory phosphorus molecule which gives energy, and then the next unit, another unit, is ADP, which is 1 phosphate less, so that's di, adenosine diphosphate, that means 2 molecules. And then the other one, which is by losing one more phosphate, it becomes AMP, monophosphate. Mono is 1. So every time you lose one phosphate molecule, it becomes one less. So triphosphate, diphosphate, and monophosphate. Now this is the process that happens, and normally in the body how it works is whenever energy comes down, the reactions, when reactions happen and it comes to the cell, and whenever energy comes down, the body will recycle and try to make more energy. That means when monophosphate is made from triphosphate, that means 3 is becoming 2 and 2 is becoming 1, and when that happens, this is 1, the body recycles and tries to add the phosphate again to make from 1 to 2, and then again from here, from 2 it again becomes 3 by adding another phosphate. So this cycle continues, and this is how normally the cycle continues. Whenever there is more energy, it doesn't do that. Whenever there's less energy, it keeps going back in cycles. It's a recycling process that happens in the mitochondria. So why am I talking about this? So normally if all nutrients make energy, and then when you burn it down like a protein or a carbohydrate or fat, any kinds of nutrients, why is it that fructose that I'm talking about, which is related to uric acid, why am I talking about all this? Fructose is unique even when you compare to glucose, because I've talked in the last few episodes that glucose and fructose are different, So when glucose makes energy in the mitochondria, it gets the energy, the ATP. Fructose differs. It actually transiently drops the energy. That means it brings down the energy levels transiently. So how does that happen? That means when 3 becomes 2 and 2 becomes 1, it gets stuck there and it goes into another cycle. And what happens? How does that happen? We'll see. So let's say glucose comes here and it goes into the cell and goes through a chain of reactions, and all the reactions again make ATP. So that's how normally glucose does. However, fructose, I'm going to put fructose in a different color. That way you know. Fructose, which is the sugar, which is a different kind of sugar that is not coming from glucose, which is like starch. This is coming from fruits, alcohol, high fructose corn syrup, honey, and agave, and many other different kinds of sugars. So this sugar, how does it behave differently, and how does it drop energy? So what it does is it goes through a series of reactions. I'm going to list that on the screen for you separately, and those enzymes will take it to this final AMP, which is 1-phosphate, that means only one, and it doesn't go back to make more energy. What it does is it takes it to it makes what is called as the one that we are talking about, uric acid. Now, uric acid here is the one that causes the problem of in the mitochondria to cause all the elevated blood pressure, fatty liver, all the downstream cardiovascular problems, strokes, heart attacks, and things like that. So how does this happen? This is a very strange phenomena that happens because it causes almost a signal, a wrong signal of something called, instead of making energy, which is going back and making more energy, ATP, 1 to 2, 2 to 3, it says don't make energy, conserve energy, and don't spend energy. So making energy in the terms of spending energy, it says no, store energy, don't spend energy, and it creates almost a signal like starvation. It creates a signal like starvation. Why? Because nature has designed this for us when we are out in the wild or in a forest, or if you are driving miles and miles together without getting food, or if you are traveling 3,000 or 5,000 miles in a journey when food is not available, or when you are dehydrated. Nature has given an alternate pathway for us to make sure that we conserve energy. So that is the kind of signal that you get to the body gets to see to make more fat and not burn fat. So that's what fructose does. And how does that happen? I will detail it a little bit more in detail for all those enthusiastic biology lovers, and also people who are more interested into the reactions, with a very little description on my next talk. I will see you soon.